welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
Welcome all to our webcast, Physical Layer Test Challenges and Solutions for MIPI Interfaces. Today we will hear a presentation by Minji Zhang, a product manager out of our oscilloscope division in US. He focuses on test solutions for mobile interfaces like MIPI and storage technologies. He is a contributor to the MIPI D-PHY and SATA working group. In addition, we also have online Robert Lashley. He is the business development engineer for EMEA to help answering your questions you may have during the webcast. My name is Jürgen Stembler, market development manager for EMEA, and happy to guide you through this webcast. For everyone's comfort, this is a lecture-style meeting. However, you can send questions in writing at any time during the session. This is a Q&A functionality of the WebEx meeting. We'll do our best to answer your questions during the session, but maybe come back to you after the session if we haven't been able to. While the answer to your questions may be published for others to see, we'll keep your identity private. Please be reminded that this webcast will be recorded so you can review and share with your colleagues at any time. At this point, I'd like to hand over to Minji to start with his presentation. Minji, please go ahead.
Thanks, Jürgen. Welcome everybody to the live webcast. We are going to discuss the transmitter physical layer test challenges and the solutions for the MIPI D-PHY and M-PHY interfaces. I'm sure we are all aware that the mobile industry is growing and that there's a need for higher performance and lower power consumption designs that are becoming ever more essential. Therefore, we have seen display panels, camera modules, application processors, memory, and RF applications adopting the MIPI D-PHY and M-PHY specifications, which offer high performance and lower power properties. So let's go over the agenda quickly. I plan to cover the MIPI overview and the conformance test requirement, followed by a brief overview of D-PHY and M-PHY electrical characteristics. Then I'm going to discuss the measurement setup challenges, the transmitter test challenges, the effect of probe and cable to measurement accuracy, and finally how to correlate physical and protocol layer issues. So let us start with the MIPI overview and the conformance test requirements. MIPI Alliance is a standard body that promotes hardware and software standardization in mobile designs. The slide shows the different type of MIPI interfaces that are supported on the mobile platform. The core of the mobile platform consists of the application processor, modem, and RF IC chips. Connected to these chips are the different applications such as camera, display, speaker, microphones, and GPS systems. On the bus, you will find the type of protocols running on the interface. For example, you will find the DSI protocol used for display panels and CSI protocol for camera modules. Finally, the different color code on the bus represents the different type of physical layers supported on the specific bus. Most of them are pretty slow, except for the D-PHY and M-PHY, which are represented in red and gray colors, which are the high-performance buses that we are going to discuss today. So in some of those buses, you will find the overlapping of the gray and the red. That means that the bus will be able to support both the D-PHY and M-PHY physical layer. Before we go to the high-speed buses, here is a quick glance of the slower buses that you will find in the mobile platform. Most of these are being used as a control interface, especially for power and battery management. And also you will find the slim bus, which is used for audio data transfer. And these are the buses that I was talking about earlier, which are not pretty fast on the mobile platform. So let's switch gear a little bit and talk about D-PHY and M-PHY. So I have put together a different view of the D-PHY and M-PHY layer and what protocols and applications that run on top of them. The earlier D-PHY layer, if you can see the slide on the left-hand side. So the earlier D-PHY layer supports only the camera and display applications, but a lot more applications will be supported on top of the next generation M-PHY. With the M-PHY delivering more performance and power savings, we have even seen other standards bodies starting to leverage the M-PHY specification. For example, the SSIC, which represents Super Speed Interchip, it's a protocol from the USB standard body that will be using the M-PHY layer to transmit USB 3.0 protocol. You will also find the UFS, or Universal Flash Storage Protocol, from the JEDEC standard body, and also the PCI Express, which they have a new name called the Mobile PCIe that will be using the M-PHY physical layer as well. The different color on the blocks basically indicates the type of test tools you will probably need for each layer. Blue represents protocol capable tools, while the green represents electrical or physical layer tools such as the scopes, the bit error rate tester, and the network analyzer. So if you're interested in testing and wonder where to start, the MIPI Alliance does have a test page containing the test resources for the protocol and the physical layers. These resources are available for members to promote interoperability. One thing to note though is MIPI does not enforce any logo requirements. The test procedures are purely informative and used only as a guidance. Third-party vendors do exist today to promote physical, protocol, and interoperability testing services. Agilent work closely with them. The test labs listed on this list, in this slide, do use the Agilent equipment in their test setup. So, we are basically very involved, right, with these different test labs to provide, reliable results for the D-PHY and M-PHY measurements. The D-PHY and M-PHY test procedures are documented in the Conformance Test Suites, or CTS. This is a very common term that you will find when you are involved in the MIPI work groups. There are 3 different sections outlined in the CTS for D-PHY and M-PHY. Section 1 covers the transmitter test, Section 2 the receiver test, and Section 3 the interface S parameters and impedance test requirements. Agilent is actively involved in the CTS workgroup discussions to provide our expertise and recommendations to these test procedures. The CTS are living documents, so they are always evolving based on the testing needs. The M-PHY CTS version shown on this slide, is currently at 0.99, and the CTS for the D-PHY is at version 1.0. We will be making some changes pretty soon to update some of these CTSs to reflect some of the new requirements that are listed, or changes in the base specifications. So that's the quick overview of the MIPI testings and where you can find the resources. Let's jump into the D-PHY and M-PHY electrical characteristics overview. So let us start with the D-PHY electrical characteristics. The D-PHY supports two operational modes. The high-speed mode, which is the HS, this is the performance mode where large volume of information needs to be transmitted, such as the pixel information on an image from a camera. So bear in mind that the camera does not transmit all the time, right? So when that is an idle, the bus go into the low power mode, or the LP, to conserve power. The D-PHY interface consists of one clock lane and up to 4 data lanes. The number of data lanes are restricted basically by the skew between the clock and the data lanes. The example that we're showing here in the slide is a 2-lane D-PHY link. The lane scalability and data rate flexibility allow the application to be designed to meet a specific performance goal. So if you need to transfer a higher volume of information, you can either scale the number of data lanes, or you can actually increase the data rate that runs on the existing data lanes. So there are some flexibility in terms of implementing a D-PHY interface to meet the performance goal. The real D-PHY waveforms that are shown in these example screenshots are taken from the positive and negative components, which are known as DP and DN, with a high bandwidth real-time oscilloscope during the high-speed and low-power transmissions. The left screenshot shows the high-speed data transmission initiated and terminated by LP transitions. The HS transmission is implemented differentially, while with the complementary signals on DP and DN. LP transmissions are implemented single-ended. The right screenshot shows an example of an LP transmission. LP transmissions are used, for instance, to turn on and off display panels. So these are the different waveforms or operational mode that you will find on the D-PHY interface. So that was a short overview on D-PHY, and next we're going to talk about M-PHY. M-PHY also supports two different operational modes which are very similar to D-PHY. The only difference is the low power mode definition in M-PHY is known as the low speed mode. Contrary to the D-PHY, there is no clock built in on the M-PHY interface. The number of data lane implemented is also not restricted, but constrained by the protocol specifications. There is no skew issue that you have to take care of on the M-PHY interface compared to the D-PHY. The transmitter supports two different drive strengths, namely the large and small amplitude swing. The M-PHY also allows optional slew rate control over its signal in order to reduce EMI emission from the bus. So the faster the slew rate, the higher the energy is emitted, but it may be necessary to maintain signal integrity on the bus. So there are a bunch of knobs and flexibility on the M-PHY interface, similar to D-PHY, that allows you to achieve your design goals and not causes any interference to your adjacent circuits. So if you remember the previous slide, I talked about there's no clock on the M-PHY interface. So how do they transmit the clock? The clock has to be embedded into the bit stream instead. The high-speed mode uses the AB10B encoding scheme, which is a very common clock recovery that you will find in many high-speed interfaces such as USB, PCI Express, and SATA. On the low-speed mode, there are two different schemes. They are known as Type 1 and Type 2. So the Type 1, which is the most common scheme, uses the pulse width modulation scheme, where the bit 1 is represented by a shorter negative pulse, followed by a longer positive pulse. Bit 0, on the other hand, is the opposite, with the longer negative pulse, followed by a shorter positive pulse. This scheme allows the clock to be recovered using the falling edge on the bit stream. That is how the clock is recovered from the Type 1 PWM scheme. The other type is the type 2, which is only used in the DGRF v4 application. Is basically a slower AB10B encoded signal with a synchronous clock in order to sample the data. It needs this additional clock because the receiver's PLL may not be able to tune or lock to the slower rate signal during the low speed mode. So these are the two. This is the different schemes available on the M-PHY and how the clock are recovered from the signals. So that was a very brief, again, very brief overview of the D-PHY and M-PHY electrical characteristics. We have, so let's, dive into the challenges. And the first topic that we want to talk about is the measurement setup. So what do you need to care about when you are setting up your, test setup to perform the measurements? So the first thing that we have to consider is how much bandwidth do we need for the D-PHY and M-PHY transmitter test. So on the D-PHY, in both cases, it all depends on the fastest rising or falling edges in the signal. So the faster the signal, the more bandwidth you will need in order to measure that high-speed edge. So yeah, that's right. So if you have a faster rise time, you will definitely need more bandwidth to measure that fast rise time. So how do we know what's the fastest rise time on the D-PHY and M-PHY? We can all go back to the spec. The spec does provide the minimum rise and fall time requirements, and by applying the fastest and rise and fall time from the spec, we can actually calculate how much bandwidth we'll need for the different data rates. So for D-PHY, there are two different range of data rates that it can be supported by the spec. The signal up to 1 gigabits per second, and also signals between 1 to 1.5 gigabits per second, and they have different rise time requirements. And using that fastest rise time requirement, we can apply the scope bandwidth equation to calculate how much bandwidth we will need for both speeds. So we need about 4 gigahertz for signal up to 1 gigabits per second, and 6 gigahertz for signal between 1 to 1.5 gigabits per second. And that's an app note that you can find that provides that how the equation is what the equation is in order to calculate the bandwidth requirement. So again, similar to what we have shown on the D-PHY, we also can calculate the the bandwidth requirement for the M-PHY using the fastest rising and falling time in the spec. The fastest edge is defined as a 0.1 of a UI in the M-PHY. So we would require roughly 6 gigahertz for gear 1, 12 gigahertz for gear 2, and 24 gigahertz at gear 3. But bear in mind that the gear 3 is currently an estimate because the spec is not officially released yet until the middle of 2013. So we are currently still working on getting the definition for the gear 3 rise and fall time. But this is but basically the 24 gigahertz is an estimate at this point. Next, we want to discuss the termination and the probing options. For D-PHY HS mode, the signals are terminated into a 50 ohm single-ended to ground, as you can see on the top left picture. For the low power mode, the signals are unterminated or open to minimize the current flow to save power. So these are the two different types of terminations that you will find on the D-PHY interface. So given these termination configurations, the first probing option is to terminate the high-speed and low-speed signals into the scope. The only downside to this option is the LP amplitude is reduced by half because LP should be unterminated. So once you terminate that signal into a 50 ohm to ground, you will basically halve the amplitude. That is one possible probing option. So the second probing option is to terminate the signals into a dynamic termination circuit, so that the termination circuit will switch accordingly to the high speed and low power mode. So when it's operating in a high speed mode, it will actually go to 50 ohm, and when it goes to low power, it will go to unterminated mode. And how do we probe? So we can use the scope differential probes to measure the signals. So the second option, I believe, is the more recommended option, because the signal level for the low power mode is correctly measured, right? Although the setup could be slightly more complex. So this is definitely two different probing options, and probing option number 2 is, I think, the more recommended way to be probing at the signals. So let's talk about M-PHY. Termination on the M-PHY is very different from the D-PHY, although from the high level they may look the same. The high speed and the low speed mode can be terminated either into terminated or unterminated mode, as long as signal integrity doesn't affect performance. In addition, the terminated mode is not 50 ohm single-ended to ground, but rather a 100 ohm differential. With this termination configuration, the first probing option is terminating the signals into a dynamic termination circuit like the D-PHY, and use the scope differential probes to measure the signal. The second probing option is terminating the signal into an open termination, and add a 100 ohm resistor across the probe tips of the scope differential probe for terminated mode, or remove the 100 ohm resistor for unterminated mode. So there are some flexibility here as well. The downside to the second method is that you can only get one of the termination configuration at any time. So because the resistors have to be permanently soldered down to your probe tips. So I get a lot of questions on terminating the M-PHY signal into the scope. So a lot of customers has been asking us whether they can actually terminate the signal directly into the scope. While they can do it, it is actually not recommended. And the reason is the scope termination does not exactly match the M-PHY termination requirement. Differentially, both the scope and the M-PHY terminations are the same, but the common mode termination is not. M-PHY termination does not terminate common mode, so there will be a higher reflection and distortion. So if the signals are terminated into the scope, the signals may look better and may not reflect the actual signal performance. So this is the reason why terminating into the scope is okay, but you may be getting a better results compared to the actual performance on the chip. So since every D-PHY and M-PHY chip has a different pinout, how do we actually put the chip, for test? That is not a standard fixture to host the PHY chip. So one of the way that you can design your own board, right, to put the chip is using the resource provided in the MIPI Alliance. So the MIPI Alliance does have resources to design a test vehicle board, or TVB, right? This allows you to put down your chip on the fixture and then hook it up for test. Schematics and Gerber files are provided as well, so that all you need to do is to lay out and route the signals to your chip, so that you can put down your PHY chip onto the board. And in my few previous slides as well, I talk about dynamic termination circuits, and you may be wondering if there's any available today that you can use for the test. So on the D-PHY, the reference termination board, or RTB, is available, and there's an FPGA built onto the board that will terminate the high speed and low power into the correct termination when into the appropriate termination, basically. So the FPGA will be able to detect what the voltage level of the signal, and will switch that termination dynamically so that you can make the appropriate measurements of the signal. The TVB and the RTB can be connected through the SMA, and the probe points can be accessed on the RTB, so you can solder down the scope probe to the RTB board for measurements. Currently, the M-PHY RTB is not yet available. The plan to create it is not clear either, so there's still some discussions that need to go on to create the termination board for the M-PHY. Finally, if you want to probe the D-PHY or M-PHY signals at the system level, you can use the scope differential probes to access the signal at the traces or probe points. So here you don't have to worry about termination because it should be already been taken care at the chip level when the chips are integrated together on the system. A huge variety of probing accessories are available, such as soldering, socket, and browser probes. So you should also consider using a probing accessories with lower loading so that they won't load down or distort the signal. These are the same options you can apply to the earlier scope differential probes for validating at the chip level as well. So they are, the loading can, some of these accessories has ultra low loading, even as low as 70 femtofarad. So it will not distort the signals that you're trying to measure. Okay, so we have covered the measurement setup challenges. So next, let's move on and discuss the transmitter test challenges. So you have hooked up to your board, to your design, and next you need to be making the measurements. So what are the challenges in the measurements themselves? So the first thing to consider is the test pattern requirement for transmitter tests. Under D-PHY, the test pattern are not defined in the spec, but the CTS does require the 0-1-1-1-1-1 and the 1-0-0-0-0-0 patterns in the high-speed mode. It also requires a signal to transition between high-speed and low power for timing measurements. If you need some references to generate these patterns, the PAT GUI reference test pattern generator tool is available on the MIPI test page. So if you can program your chip to transmit, the pattern, and you're wondering what pattern to send, you can use the PAT GUI tool to generate that pattern file for you. So you can also use it to generate various packet payload data format and line length as required, for the transmitter test. So once you're able to generate the required test pattern and signal conditions, now you have to go and perform the measurements. The CTS requires the following tests, including the high-speed and low-power electrical characteristics, such as the common mode, voltage, and rise-fall time measurements. The other set of tests are the timing measurements on the clock and data signals that you have to measure as well, especially going from low power to high speed and high speed to low power transitions. So if you look at the list, right, this is a pretty huge list. And Agilent do provide the D-PHY application that can automate all these measurements. This is by far the more efficient way to analyze your design than making all these measurements by hand. Yep. So I just want to highlight something on the D-PHY. I think the timing measurements are really emphasized on the D-PHY interface because of the termination on the receiver that has to switch dynamically to the terminated and the unterminated mode. Because of that, there's a huge list of timing requirements that the signals have to meet for the interface to work correctly. So there are many different timing requirements, as you can see on this timing diagram, that you have to meet. Again, the D-PHY app, right, that the Agilent offer can automatically make all these timing measurements to save you time. So contrary to the D-PHY, the required test pattern are specified in the M-PHY spec. Right, the two test patterns are called the CR pad and also the CJT pad. The random payload used in the CR pad is suited for transmitter tests because it stresses the transmitter amplitude and jitter more than the CJT pad. So in addition, the M-PHY transmitter has to support both continuous and burst CR pad mode. These are the conditions that you need in order to do the transmitter test. The CJT pad, right, is used mainly for the receiver test because the transitions between lower and higher data rates in a pattern can more appropriately stress the receiver's ability to lock into the quick change in frequencies. So these two patterns are used in different test conditions because of the properties in the test pattern. Again, once you're able to generate the required M-PHY test patterns, you need to proceed to perform the measurements for the high speed, the PWM, and the sysclock test parameters. The test parameters again include amplitude, slew rate, skew, jitter, and unit interval measurements. The jitter test on the high speed signals constitute of both long-term and short-term total jitter and deterministic jitter that is used for characterizing the bursty nature of the M-PHY signals. So Agilent has an M-PHY application to address this measurement based on an older CTS. So we are currently adding new tests and updating the existing tests with the latest methodologies, of the CTS that will become official 1.0 pretty soon. So that is what we are doing right now in order to support the M-PHY. So the M-PHY testings. So finally, here is the example of a few screenshots of the automated transmitter conformance application from Agilent to address the D-PHY and M-PHY measurements. The application have a task flow that will guide the user through configuring the DUT, selecting the test, hooking up the signals, and executing the test. Once the tests are completed, the application will report a pass or fail for each of the test items, as well as generating a HTML report for easy sharing and results filing. So So this graphical user interface are standard for all our applications. So once you know how to use one of these conformance tool, you will know how to use every one of them, because the other applications that we provide, such as addressing the USB and SATA test requirements, uses the same graphical user interface and task flow as well for doing the test. So that's the transmitter test challenges. Next, I want to talk about the effect of probing and what's the impact on the measurement accuracy. I think this is a very common issue that many find in their test environments, right? The probe and the cables, affecting their results. So how many times have you actually picked up a pair of matched cables or probes in the lab and later find out that their responses are not matched? The two plots at the top show the response of two matched cables pair that do not have similar response. The first cable shows a typical insertion loss performance with the bandwidth of 10 GHz, but the second cable shows a huge frequency bump, reducing the bandwidth to about 5 GHz. So if you are using this cable pair in the measurement, this can cause unnecessary signal distortion because of the mismatch in frequency response. Bottom left scope screenshot show the distortion caused by a mismatched cable pair because the frequency bump changed the characteristics of the measured signal. Because of that bump, you do not get symmetrical response or the symmetrical waveform on the differential pair. So what the effect of that is, when you're making a V peak-to-peak common mode measurements, it could be 10 times worse than the voltage when you are measured with a well-matched response cable pair. So this is one of the common issue that I've seen that could be causing some probing issues. So the other problem that we normally find is the skew in the probes and cables. That can be a major problem as well. So you take a pair, a well-matched pair cable in the lab, and again you find that the skew is not very well matched. So the lab screenshot shows a pair of cable with no skew, and the V peak-to-peak common mode measured about 32 millivolts. So that is pretty low. But once you add a skew of just 5 picoseconds in the cables, and this is not uncommon even in a pair of matched cables, there can actually, the V peak-to-peak common mode results can be increased by threefold. So this can have a huge impact to the measurement accuracy when you're making measurements or characterizing your board. So here is an example of the impact of probe with unmatched frequency response and skew to the M-PHY power spectral density measurement. This test meant to constrain the common mode emission, which has to fall between the PSD limit curve. But the effect of the probes can cause failures that are not attributed to your design. The left screenshot shows the passing results from a well-matched cable, but the right screenshot shows it fail when you have a mismatched probe response and a mismatched delay on the cable that you're using for the measurements. So this is not attributed to your design, but rather the probing or the measurement setup themselves. And here is also a very common problem, right? How many times do we have to modify our probes in order to for accessibility, right? So when there's a problem reaching to the probe points, right, we have to figure out some ways to be able to reach those probe points. So if you look at this screen here, right, the scope vendor does not provide any correction files, for this configuration. So how do you know that the measurements that you are making are quality measurements? So that's another big challenge. So one of the common way that you can overcome this is to do the correction using the VNA and the S parameter models. So there are definitely some steps you have to take here in order to to correct for the probe. So you need to first locate a VNA. You need to find somebody who knows how to use the VNA. You need to create the S parameter models, save the models into a thumb drive and load it into the scope, apply the correction and response and delay in the scope, and then analyze the data. So these are not a simple task, right? It can take a while, to get to generate those files to correct your signal. So there's a huge effort and time involved here, and this is possibly why most of us tend to ignore the probe and cable loss entirely, and that we assume that the cables are well matched and well behaved. But in reality, right, that may not be the case. So, we have actually a new innovative way that you can reduce the characterization time and effort significantly, right? The feature is called the precision probe, which allows you to characterize and correct in 3 easy steps using just the oscilloscope. So there's no VNA or any other instrument involved here except for the oscilloscope. First, you measure the baseline using the cables that are provided. So without any cables added to your measurement path, what does the signal look like? So you have the baseline. So second is you will add the probe and cables you're going to use in your measurements that you added in between the cables. So the response that the scope generate and measured is now different, and based on the baseline and the measurement with the probe, we can actually characterize what that insertion loss of the cable is and the delay, and then we can correct that. And the third step, right, is basically saving the correction file into the scope and use it in your measurements. So this method here is really fast. It also saves you a lot of time, and you don't need to have all the VNA expertise to run this correction. So this is a screenshot of the precision probe, right? The precision probe shows the original response of the probe and cable in blue, in the blue plot, after performing the characterizations, right? Then the precision probe applies a correction filter in yellow to the original response to correct and normalize the response shown in the purple. So by applying the blue and the yellow curve together, right, you get a normalized flat response. It not only corrects for the magnitude, but also the phase of the insertion loss in the cable. The skew and the probes are now perfectly corrected and matched. So no matter what combination of probes and cables that you're using in your lab, precision probe can definitely correct the response and skew so that they match up in all your measurements. So there's no difference between using from one cable to another. So this is a great way to achieve consistency and repeatability in your measurements. So here is just a result before and after precision probe is applied. In some instances, the cable have a lot of insertion loss, and it can actually slow the signal down to 67 picoseconds. So once the precision probe has been applied, the rise time is corrected to the 21 picoseconds, which actually reflects the true performance of the signal. Okay, so we talk about the probing issues and what kind of solutions is available. Next, we're going to talk about how we can correlate physical and protocol layer issues. So while the scope, right, is actually a physical layer tool, the MIPI protocol decoder on the scope, is able to decode the symbol and packet of the D-PHY and M-PHY signals. And you actually use this capability, right, to correlate the physical layer performance with the protocols. Various protocols are supported today. For D-PHY, we have support for CSI2 and DSI1 protocols. For M-PHY, we support the GRF v4, UniPro, LLI, and UFS protocols. It also has the ability to decode multiple data lanes on the interface, as well as displaying details information in the packet. The scope protocol decoder is not a replacement for an actual protocol analyzer, but can be extremely useful for troubleshooting signal integrity related problems. The D-PHY protocol decoder that are shown in this slide is an example of a DSI1 protocol decode. The blue and the red provides a quick differentiation over the control and data packet type. The decoded packet are displayed on the analog display as well, at the right below the waveform, so you can correlate the packet with the analog waveforms. Detailed packet information and timestamps are also shown in the table for each protocol packet as well, so that you can look at the content in the packets. So the M-PHY protocol decoder shows shown here is a simultaneous UFS and UniPro packet decode on the analog waveform. You can observe that the UFS write command in the top waveform, which is encapsulated inside the UniPro TC0 data frame. So as we all know, UFS is a higher level of the protocol application layer than the UniPro, and the scope decoder can actually decode both the information simultaneously. Okay, the table below can also be switched back and forth quickly, between the decoded UFS and UniPro packets, so that you can quickly go back and forth, right, and look at the correlation between those different protocols. In addition, the MIPI D-PHY and M-PHY scope decoder will also compute the CRC from the received bits and compare it with the actual CRC embedded in the protocol frame. If there's an error in the protocol, the decoder will flag it to the user for further troubleshooting. So what you are seeing here on this slide, the CRC are all showing good, meaning that the received data and also the CRC embedded in the packets, they are matching up. So there's no flag or there's no error warning in the packets. However, in the case that there's an error, the protocol decoder will be able to flag it. So on the left-hand side, you will be able to see that the protocol and the ECC and the CRC are received properly. So you didn't really get a warning from the decoder, right? So it means that the signal integrity is good and the packets are received right as it is expected. However, on the right-hand side, when there's an error, a bright red color warning will be displayed on the packet, so that user can know that there is a problem, that the bits are not received correctly, and then we have to go in. We can now go in and debug it. So you can by observing the analog waveform and also the decoded packets, we can actually figure out what's actually causing the problem. Is it really a protocol issue, or is it really a signal integrity issue that's causing an error? So this is a great way for you to debug issues on related to protocol and physical layer. The protocol decoder also supports search and trigger functions, right? It allows you to search the analog waveform for specific packet type with customizable field. So if you are looking for certain packet information, right, you can set up a trigger, and the scope will be able to find that in the analog waveform. The trigger function only show the waveform when the packet conditions are met. So you can also stop the scope right once the protocol trigger condition is met. So and finally, you can set it to trigger on any error or specific error that you're looking for. So this is very flexible and a powerful way for you to find the packets that you want to locate in your waveform. All right, so we are coming close to the summary. So Agilent has the test solutions, right, that provides a complete coverage to the MIPI validation needs. Here is just a slide showing what we offer. For the physical layer testing, we have tools for transmitter, receiver, and impedance/return loss validation. Using transmitter tests, under the transmitter test, Agilent has the scopes, the electrical applications for D-PHY and M-PHY, the probing solution for probing at the signals, as well as the precision probe for correcting the loss and skew on the cable and probes. For the receiver test, we have the different birds, the J-bird and the PAR-bird, and also the automation for characterizing the receiver. And on the impedance and return loss side, we have the ENA with the option TDR, as well as the wide sampling oscilloscope for characterizing the reflections, impedance on your circuit. And on the protocol validation, we have the protocol analyzer and exerciser, as well as the scope protocol decode for various D-PHY and M-PHY protocols. So this is the list of the solution that we provide, and I think the automation that we also offer in this solution, right, can eliminate days and sometimes months of testing and debug, if we are to do these measurements manually. So we try to add value wherever we can, to help the customers be more efficient and maintain the accuracy they need for their validation. So in summary, the mobile trend is driving the needs for higher performance and lower power designs. D-PHY has been adopted in most camera and display interfaces today, but the next generation M-PHY will be even more widely adopted for different applications, including standards outside of MIPI ecosystem such as JEDEC, USB, and PCIe SIG. So Agilent is driving the specification and testing discussions with the MIPI workgroups and test houses, as well as the key standard ecosystems as well. So Agilent is involved, right, very deeply in the MIPI applications because we see this is as an important area in the next few years. All right, that's pretty much the end of my presentation. Thanks for joining us and your attention. So I'm passing this back to Jürgen.
Thank you very much, Minji. This was really great information you shared with us here. And as Minji mentioned here, and you see on the screen, it's now time for questions. We received a couple of very good ones, but you can still send in additional questions in writing through this Q&A functionality on the bottom right side on the screen. We'll do our best to answer these now directly. Robert, can we now go through the questions you collected, please?
Yes, thank you, Jürgen. Minji, for the first question, would you mind going to slide 17? It deals with that slide. So the question is, does the 50 ohm series resistor represent the output impedance of the driver or the characteristic line impedance?
That's the output of the driver and the characteristics of the channel as well. So there's a need, right, to maintain that 50 ohm from the output of the driver across, and the on the trace. So that's kind of the 50 ohm environment that has to be maintained on the D-PHY line. So this is why, when you want to characterize, so if there's any discontinuity, right, on that line, you will find reflection, and that could distort the signal. And this is why some of the S parameter and impedance measurements are required in the CTS, just to make sure that you don't have any excessive reflection out of your board that can distort, right, the performance of the design.
Okay, excellent. Why doesn't the MIPI Alliance enforce certification requirement? It seems like a great way to enhance quality of products.
I think there are a couple of reasons to that. The first very obvious one is that it's an internal bus, chip-to-chip interconnect. There is no external interface like the USB or SATA that you can hook up different devices to. Because of that, product interoperability is guaranteed between the chip vendors and the system integrators. It also reduces the implementation costs. Enforcing the test can be very expensive for companies to get into the technology. So that's the reason why. Having said that, right, there are some other applications that I mentioned earlier. You heard about UFS, SSIC, mobile PCIe, right? Those are not MIPI standards, so they have the right to actually enforce certification requirements in those standards. But that is something outside of the charter of the MIPI Alliance.
Okay, thank you. The next question, is the precision probe feature supported on the electrical test packages?
Yeah, the precision probe is definitely supported in the automated software that we provide. So we understand that you have a need to make better measurements, right? Not only by hand, but also with the automation tool. So we do incorporate that feature and capability into the application for better measurement accuracy. Yes, we do.
Okay, great. What is the difference between the scope protocol decoder and an actual protocol analyzer?
Yeah, I think this is a great question. I get this a lot, asking about, can I replace the analyzer, right, protocol analyzer with a scope protocol decoder? I think the answer is actually no, because they are two different specific instruments. Just to start with, right, there are two limitations, using the scope protocol decoder, right? I mean, scope protocol decoder is a very good way to debug and correlate physical and protocol layer issues. There are definitely some limitations there as well. The two things are the memory and the hardware trigger, that the protocol analyzer offer. So memory is associated with the trace capture, right? Scope is an analog tool instrument, right? When it saves the waveform, right, it saves it with many bits, and because of that, right, we are limited by how long the trace that we can capture. But on the analyzer, right, we only capture zeros and ones, so the analyzer can actually capture a really deep trace for analyzing your protocol. And the other thing is the analyzer can have a hardware trigger that can trigger on specific protocol packets. This is something not available on the oscilloscopes.
Okay, thank you. Can the scope protocol decoder decode M-PHY low-speed PWM packets as well?
Yeah. So, yep. So maybe it's not very obvious in my slides. The protocol decoder that we offer, right, for the M-PHY can recover the clock from the high speed, as well as the PWM and sys clock as well. So this is very important because without the right recovery method, right, we are not able to sample the data correctly and feed that into the decoder, for decoding the packets. So yep. So we do support the multiple schemes that I talk about, HS, PWM, and the sys clock. So all this we can recover and decode, right, the packets from these different schemes.
Okay. What's Agilent's plan to cover other MIPI protocols?
Yeah. So I guess the questions is asking whether we're going to support, not only maybe on the M-PHY, right? There are different protocol decoder like SSIC and mobile PCI Express, right? So we are definitely working with our key customers to develop these protocols. In fact, we also are working on providing the code for the lower speed interfaces as well. So we just launched the RFFE protocol decode. So that bus, right, is used to control the front end RF circuit and the low noise amplifier. So we are not only limited to the M-PHY protocols, we are working on to create and work with our customers to develop the lower speed protocol interfaces as well. So if you have a need, right, just go out to the audiences here. You have a need, yeah, feel free to contact us, and we'll be happy to work with you. Right, to develop some of these capabilities.
Okay, thank you, Minji. With that, due to time constraints, I will pass it back to Jürgen.
Thank you very much, Robert, and thank you very much for this question. It was really great. If you have any further questions after the event or you want to ask these offline, don't hesitate to contact us on the addresses provided. Additional information like application notes, data sheets are available on our website. I would like to repeat one statement here. It was mentioned on the last slide from Minji. There's a whole value chain of requirements, test requirements coming from receiver, protocol, transmitter, and Agilent, as you can see, and I hope you have seen on this presentation, is really one of the suppliers for design up to compliance tests for all the different portions, like transmitter receiver test, and also for the receiver test. There's a lot of things available on our website for application notes and so on. So please don't hesitate to contact us and to look on our websites.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.